Deep learning has come a long way since the multi-layer perceptron days, where we have seen that evolution from single-layer perceptron to multi-layer perceptron gave a boost in terms of being able to capture a generalization of a large number of functions with nonlinear kind of constructs. Since then, there's been an explosion of work in the context of deep learning via inventions of several variants of the basic perceptron, and we see several evolution of these networks for different purposes. So we just cover some brief examples of neural networks which are now currently being worked on and which are the basis for the current success of deep learning. All of them work on the same principle that you have to ultimately generate a stable neural network with weights as part of it stabilized so that they're able to perform prediction function for or classification function for any future data. So as we saw, deep learning basically is able to abstract out layers of abstraction, right? Where, for example, we looked at abstracting from edges to parts to collection of parts to something like a face. So this is one simple abstraction, right? So any kind of abstraction like this basically forms it in layers of neural networks. So any neural network, as you know, is made up of a collection of neurons. Each neuron is, as we saw, like a simple TLU or a variant of that, threshold logic unit or a variant of that. So what typically will have is every neuron will get multiple kinds of, inputs and each input connected by an arrow with a weight. Then there is some kind of an activation function, and output will be after you do sigma of wi xi, you look at how the sum actually is applied to activation function and the output is obtained. So this is how a single neuron starts to behave. So what happens in a neural network? A neural network basically has to start with a input layer, then it has one or more hidden layers where there is connectivity between the input and the first hidden layer to second hidden layer, and so on. Ultimately, you may reach probably, say for example, for a spam filtering case, you only have the output is only spam or non-spam, right? So what happens is there are two passes which happen in one pass of a deep learning network. First, suppose you are given one data of input, and what happens is based on initially a random collection of weights in the network, you initialize the network. You try to compute values at each node by applying the corresponding sigma wi plus the weight basis and a corresponding activation function for each node. Then use them as input for the next node. You compute the output here. Then you keep getting the output at the output layer, and you try to find out from a labeled data if something is already a function here. If suppose the label was supposed to be 1 or 0, you look at how far is from 0. Suppose it's supposed to be ideal value is 0, and you get a value like 0.12. So here, this is what is known as the error. What is happening with the error now? It's never possible that in one pass for an input, you'll always get exactly the value which is the target. So there we find that this is what is known as the error which is obtained in the forward pass of a deep learner. And then when we want to come and redo the network, we use a phenomenon called backpropagating the error back to update the weight. So backpropagation is a simple technique by which the weights of each of the layer connected to the output layer is updated based on the error and updated to new weights. These weights are again propagated to the next layer, next layer, next layer, and so on. So what happens in the end is you get updated weights after one forward and one back propagation loop, and this together is done for one input row. Once you repeat this forward and backward loop of forward, computation of functions from activation functions layer after layer and computing the error, then error back propagation done one layer, forward propagation and backward propagation for one input value. Then you do it for the second input value. You do it for the entire input data which is there in your training set, and that is called one epoch. So once you do this over one epoch and you see a stabilization of the error, or if it's not stabilized to some level of threshold which you have obtained, means threshold should be less than say 0.01 or 0.05, 5% is your error for classification. Then you rerun the entire thing again with updated weights. So if you see the life cycle of deep learning, the way it works is it takes one input row, computes the forward loop, computes the error, back propagates the error to update the weights, then runs it for the second example, third example, till examples in the training set are over to one epoch. It goes on for multiple epochs till you reach a stabilization where your guarantee of error within some threshold which you obtain. Or you can put a limit of number of epochs. Then you say that, okay, training accuracy is so and so, and then the collection of weights of the nodes which you obtain in the final stabilized network is your model. That's the deep learning model you learned for your target input classification problem or for your regression problem. So this is how deep learning actually works in practice. But if you see here, deep learning works in a model which is basically a forward loop. Means there are only forward arrows from one layer to the next. So such networks are called feed-forward networks, are the most common networks which we use typically for image and video kind of a data, where we don't have to worry too much about any kind of memory in the network, etc. So most common deep learning formalisms are feed-forward networks, and one special version of feed-forward networks called CNNs, which is convolutional neural networks, are basically a step before it where you take raw images and run through some transformations before they fed into a feed-forward network. It's called convolution step and has been proven to be very useful for image and video. But at the core, they are feed-forward networks. But what has happened in speech and text scenarios is there is a need for memory to be present in the network, and that is only possible if you can allow cyclic arrows or backward arrows in the network. And that is where we have evolved a new form of network beyond feed-forward networks known as recurrent neural networks or RNNs, and special variants called LSTM, long and short-term memory, which are variants of the core network but which allows loops within the network so that it can allow for memory to be present in the network, and this has been proven to be very effective for text and audio, etc. So what we need to see is deep learning network at the base is basically a series of forward propagation, backward propagation, iteratively done till you reach a certain qualified error. The topology of the network is dictated by what kind of input we're talking about. If it's image or video, we look at feed forward. If it is text or speech, we try to look at RNN kind of a network. So deep learning today is very successful because of a lot of revolution in the way topologies of the networks have been designed and fine-tuned for each of the different kinds of media and how they are successful in their own contexts.